Welcome to another informative series on electric motors. In our last video, which is the first part on stepper motor, we look at how a permanent stepper motor works. The way these motors were designed was looked at. Finally, we ended off looking at their application in an industrial use. In today's video, which is the concluding part on how stepper motors work, we will be looking at reluctances and hybrid stepper motors respectively. The way this motor works will be looked at, and their applications. Stay tuned. Variable reluctance stepper motor, on the other hand, is made up of a non-magnetic rotor. The design of these motor is the simplest among the three stepper motor that was mentioned earlier. That is, it is made up of soft iron, a non-magnetic, and a toothed rotor. Hence the reason why it is the cheapest. Because the rotor is not magnetized, there's no magnetic attraction between the rotor and stator when the stator windings are not energized.
The soft iron of the rotor is made up of a ferromagnetic material, such as iron. This ferromagnetic material is used for most magnetic cores. That is, because of the abundance of ferromagnetic material readily available on Earth, and its ability to pass magnetic flux easily. However, a variable reluctance stepper motor has no magnets rotor, which means it cannot output holding torque or detent torque at standstill.
The advantage that a variable reluctance stepper motor has is that there is no need to change the polarity of the stator poles. So, the drive circuitry is a little bit simplified.
Again, there is a limiting factor here. Because the rotor is not made from permanent magnet, the torque produced will be less when compared with the permanent stepper motor. And there is no detent torque at standstill. So when the coil is energized, an electromagnet will be created which will cause the soft iron rotor to align with the electromagnetic poles. However, when aligned, one of the teeth of the rotor will be left unaligned in the air gap. This is deliberately done in such a way that, when the next coil is energized, the rotor tends to move to the energized coil, which is because the unaligned teeth in the air gap are very close to the unenergized magnetic poles. For example, let's look at this 50-teeth rotor and stator design. This is a 4-phase stepper motor where the coil is divided into 4 sets. Inputting number of poles is 50 and the number of phases is 4. So when the motor is energized, this would result in a step angle of 1.8 degrees.
I am pretty sure that this motor will not be as expensive as its permanent rotor counterpart. So the motor required some relatively high-speed applications with less torque. This type of mid-range application is what fits the variable reluctance stepper motor. And it should be perfect.
Their dynamic torque production is relatively low, but they have less torque drop-off at higher motor speeds. So for mid to high-speed applications, they are often a better choice than permanent magnet designs. However, variable reluctance steppers are known to produce high noise levels, so they're not suitable for applications where noise is a concern.
A hybrid synchronous stepper motor is a combination of a permanent magnet and variable reluctance designs. Hybrid stepper motors have a permanent magnet, a toothed rotor made from 2 sections, or cups, which is opposite in poles and whose teeth are offset from each other. The electromagnetic stator is also toothed. The rotor teeth help guide the magnetic flux to preferred locations in the air gap. This will improve their holding, dynamic, and detent torque when compared to permanent magnet and variable reluctance types.
With the strong permanent magnets that the rotor is made of, and toothed rotor, a toothed stator, and a tiny air gap, the stepper motor is able to focus the magnetic flux better than the permanent magnetized stepper motor and variable reluctance stepper motor.
The rotor design makes it possible for greater torque to be delivered as a result, which is because the teeth are offset from each other. Again, one thing worth noting is that the stator teeth are always lesser than the rotor teeth, which means there is always a tooth or two teeth held unaligned in the air gap at any point in time. This will make the stepper motor to deliver an even greater precise rotor movement.
Now let's look at how the motor is constructed. The construction of a hybrid type stepper motor starts with two rotor cups, which are rotor 1 and rotor 2. And a strong rare earth permanent magnet which is axially magnetized. So in the market today, there are two common types of rotor design. This are 50 teeth, which will equate to 1.8 degrees axial step, or 100 teeth, which equate to a 0.9 degrees axial step on the rotors. One rotor is magnetized as the North Pole, and one rotor is magnetized as the South Pole. Each tooth on the rotor cups becomes a magnetic pole. Since there are 50 teeth, the full pitch is 7.2 degrees. The two rotor cups are offset by a half pitch of 3.6 degrees. So the South Pole teeth from rotor 1 line up in between the North Pole teeth from rotor 2. From a cross-sectional view of the rotor, you can clearly see that the North and South Pole teeth are alternating, which is because of the offset of the two rotor cups. When the windings are energized or excited by the driver, the stator poles turn into electromagnets, and the permanent magnet rotor will follow them by both a pull and push effect and stops at fixed increments. The north poles from the stator will attract the south poles from the rotor, and vice versa. There are 8 stator poles in the stator. When windings are wound to the main poles and a current is applied, each pole is magnetized to the north pole or the south pole. The direction of the current can determine the magnetic polarity. When excited, 2 poles at opposite sides have the same polarity, and 2 poles positioned at 90 degrees from these poles have the opposite polarity. The main poles excited together are called phases and can be divided into 2 phases, which are phase A and phase B. And it is on these bases that it is called a 2-phase stepper motor.
And it is on the basis of this reason that hybrid-type stepper motors rotate 1.8 degrees per step. That is, the motor only moves a quarter of a tooth pitch per step. This is due to the geometric design between the rotor and stator.
So when phase A is excited as the south pole, and its stator teeth are directly aligned with the north pole teeth from the rotor, the stator teeth of phase B are actually offset from the teeth of the rotor by 1.8 degrees. This is called the teeth arrange offset and is the reason why a 2-phase hybrid-type stepper motor rotates 1.8 degrees per step. For a 0.9 degrees per step stepper motor, both the rotor teeth need to increase to 100. And anything more than 100 teeth is quite difficult to manufacture.
These days, with hybrid stepper motors, high torque can be obtained by the rare earth permanent magnets. Also, high resolution can be obtained by the small teeth of the rotor. Now the relationship between current and torque is close to proportional, thus making it easier to control than a variable reluctance stepper motor. Hybrid stepper motors can also achieve higher resolution. That is 0.72 degrees per full step per 500 steps per revolution. And even higher resolutions can be achieved by micro-stepping. In the coming video, we will be looking at motor connections. The way these motor connections are usually carried out will be looked at in detail, and their applications. Hope you have learned something new today. See you at the next one.